Is the screen sharing with you?
Yes, ma'am.
Okay, so we have completed mechanical properties of solids in the last class, yes?
Yes, ma'am.
Have you
Yes,
gone through the chapter and revised it?
Yes, ma'am.
Okay. See, now I told you in the beginning only, bulk properties of matter consist of 2 chapters. First one was mechanical properties of solids, which we have covered in the last class. Let's begin with mechanical properties of fluids now. See, mechanical properties of fluids also consists of two parts. First one is hydrostatics and the other one is hydrodynamics. So hydrostatic means the study of properties of fluids when the fluid is at rest. And when the fluid is at motion, we will be discussing that in hydrodynamics. So the branch of physics which deals with the study of properties of fluids at rest is called hydrostatics. Now, for an ideal fluid is that kind of fluid which is incompressible. The fluid which is incompressible is called an ideal fluid. So fluid means substances that can flow. Basically, the fluid means substances that can flow. So it includes liquid as well as gases. These come under fluids. Fine. So let's see now the concept of thrust comes. Thrust is the perpendicular force applied to the surface. For example, this is a container I have. These are the layers of the fluid. Now the fluid must be exhibiting some force on the walls of the container. So this perpendicular force, making an angle of 90 degrees with the wall of the container. This force is known as thrust, the force perpendicular to the surface. Force perpendicular to the surface is known as thrust. So the total perpendicular force thrust exerted by a liquid at rest on a unit area of surface in contact with it is called the pressure of the liquid surface. Means this force or the perpendicular force, or we can simply say thrust. This perpendicular force or thrust acting per unit area means in 1 meter square, the total force that is acting in perpendicular direction or normal to the surface of the container, that force per unit area is known as pressure. Is it clear?
Yes, ma'am.
See, so what shall be the SI unit according to you? Force upon area. We have discussed this.
Newton per meter square or Pascal?
Or Pascals. Yes, right. We have done this. See, the same SI unit was for stress as well. Force per unit area.
Yes, ma'am.
So SI unit will be Newton per meter square or Pascals. Or CGS unit would be dyne per centimeter square. For Newton, for force, the SI unit, the CGS unit is dyne, and the SI unit is meter. And the CGS unit for length or area would become centimeters. So I hope this portion is clear to you. And these are the applications of pressure, as in pressure is inversely proportional to area. You can see it from this formula. So these are the applications, like nails and pins have pointed ends. So area is very less, this increases the pressure. Similarly, wide wooden or concrete sleepers are placed below the railway tracks. If the area increases, the pressure would decrease. Buildings have wide foundations because the area increases, so the pressure decreases.
Yes,
and it is painful to walk on road covered with pebbles having sharp edges because the area is very less. So pressure increases. Fine, just note this.
Okay, ma'am. Ma'am, the screen is blank. Ma'am.
The screen is not visible. Just
No,
a
ma'am.
second, let me share it again. Zoha, is it visible now?
Yes, ma'am. Now it's visible. Ma'am. Then, ma'am.
Now comes a quantity, atmospheric pressure. So for understanding atmospheric pressure, you have to know what is atmosphere. So you must be aware of this term atmosphere. Atmosphere is basically the envelope around the Earth. This is the Earth's surface, then the gaseous envelope, around the Earth. You must be aware that the Earth's atmosphere is mainly composed of nitrogen 78% and oxygen 21%, and it also contains other impurities such as carbon dioxide, neon, and dust particles, and all these. So see, the atmospheric pressure, basically what happens is that the density of air decreases as we go up from the surface of the Earth. So therefore, atmospheric pressure is maximum on the Earth's surface and goes on decreasing as we go up from the Earth's surface. So since the density of air is not constant, we are not able to calculate the uh, density, atmospheric pressure accurately. But we have a device, barometer, which measures it. So the measured value of atmospheric pressure on Earth is exactly 1.013 into 10 to the power 5 pascals. And you have to learn this because many a times it won't be given in the question. Okay,
Okay, ma'am.
I want to ask you, I have told you just now that the concept of thrust, that particles, molecules of the fluid exert force. Yes, I've told you this. So can you tell me why the fluids at rest exert force or the thrust on the walls of the container? Any idea?
Ma'am, is it due to surface tension, ma'am?
No, not surface tension. See, what happens is that, let us take this as the container, and it must be comprising of the fluid. Now what happens at a temperature greater than 0 Kelvin? What happens is that due to thermal energy, or you can simply say kinetic energy, the molecules collide among themselves, and because of this thermal energy only, they collide with the walls of the container. So I shall write it down for you. All molecules at temperature greater than how much? Greater than 0 Kelvin
0 Kelvin.
have thermal energy. Or you can also say kinetic energy. So because of this kinetic energy only, due to this kinetic energy, they collide with the walls of the container. Start noting this down.
Done, ma'am.
Now see, we have been talking about the pressure that has been exerted by the liquid column. We have been talking about this. Now let us calculate this pressure. So consider the cylinder of the cross-sectional area A. I've already written for you. The cross-sectional area is A. And the density of the liquid is rho. We have taken rho. So what happens? A normal force acts on the bottom of the cylinder due to the weight. Let us take this height as h. H is the height of the water column. This h is not the height of the cylinder. All right, height is still the upper surface of water. Fine. So we have taken this as h. Now see, F is the force applied at the bottom of the container due to weight. Now, can you tell me the formula for pressure?
F by A, ma'am.
Yes, exactly. F by A. It would be F by A. And see, force is due to weight. Means mg. The value of weight is mg. So can we write mg instead of F? Mg by A. Can this be the formula for pressure? Yes?
Yes, ma'am.
Okay. Now, density is equal to mass by volume. We have to eliminate this mass. So we can multiply density with the volume, right?
Yes, ma'am.
All right. Now we have to eliminate this volume as well. So do you know how to eliminate this volume and insert this height? See, volume is given by the area multiplied by the thickness.
Yes, ma'am.
So mass is equal to density would remain as it is. Volume would be the area multiplied by the thickness. So what is the thickness over here? It's the length of the water
Height.
column or the height. Exactly, height. So it would be height. Rho A. Is this portion clear? So can
Yes,
we
ma'am.
put the value of mass over here? So what would be? Would be rho AHG divided by A. Area would cancel this area and we are left with rho GH. This is
Yes,
the
ma'am.
pressure exerted by a liquid column and this is also called gauge pressure. Now see, what would happen is that not only this liquid will be exerting pressure on the walls of the container. We have just discussed about atmospheric pressure as well. Yes or no?
Yes, ma'am.
So there would be an atmospheric pressure as well. So now the absolute pressure would be equal to not only the pressure exerted by the liquid column, but the sum of the atmospheric pressure as well as this gauge pressure. Atmospheric pressure, I should write it in words. Atmospheric pressure plus the pressure exerted by the liquid column. So P would be P naught, means the atmospheric pressure. And what was the value of atmospheric pressure?
No, 1.013 into 10 raised to 5 Pascal.
Yes, and mostly you would be needing that 10 to the power 5 pascals only, plus rho GH. So this is the formula. Just note this down, then we'll do a numerical on this topic.
Okay, ma'am. Then, ma'am.
Okay, I'm writing down the question. Just try it.
Okay, ma'am.
Do you know the density of water? Yes, Zoha? Do you remember? Do you know the density of water?
Ma'am, I have learned, but right now I'm not recalling it.
Okay, I'll help you. The density of water in the SI unit is 1000 kg per meter cube. And if you want it in serious unit, that would be 1 gram per centimeter. Fine. First two parts are very easy. Even
Yes,
third
ma'am.
part is not so tough. Just try this.
Okay, ma'am. Ma'am, the absolute pressure is 104.1 into 10 raised to 5 Pascal, ma'am.
How much? Can you repeat it?
104.01 into 10 raised to 5 Pascal.
Yes. That's right.
Okay.
Try it for the gauge pressure as well. It won't take much time because you have calculated this already.
Yeah, ma'am. Ma'am, 103 into 10 raised to 5 Pascal.
103
Into 10 raised to 5 Pascal.
to 10 raised by 5 Pascal. See, how did you do the first part?
Ma'am, I used the formula.
Of the absolute pressure, P is equal to
Yes,
P
ma'am.
naught plus rho GH.
Yes, ma'am.
Which value of G did you take? 9.8 or 10?
10, ma'am.
10 only, no? See, P would be 1.01 into 10 to the power 5. This is for the atmospheric pressure. Plus rho would be 10 to the power 3. This one. Density of water into 10 into again 10 to the power 3. The height is given, I think, 1000 meters. Yes.
Yes, ma'am.
So this would be 1.01 into 10 to the power 5 plus this whole term 6 plus 1 7 plus 10 to the power 7, right? So
Yes,
pressure
ma'am.
would give you, if you take 10 to the power 5 common, this would be 1.01 plus 10 to the power 2 will be left. So this is around 1.01, not 1.01, it will be 10. This would be around 101. 101.01 into 10 to the power 5, which was similar to your answer. This was 104, you said. And this was for the first part. Now for the second part, see, P minus P naught is equal to rho GH. Yes. And what was gauge pressure? Gauge pressure was this only.
Yes, ma'am.
So only this portion is rho GH, which is the gauge pressure.
Okay, ma'am.
All right. So you,
Yes.
how did you do? You've subtracted something from this.
Yeah, ma'am.
See, rho would again be 10 to the power 3, G would be 10, and H is 10 to the power 3. So this would directly give you 10 to the power 7 pascals, mean this term.
Yes, ma'am.
That's why I was saying you don't have to calculate.
Yeah.
Right? Just try this C part.
Okay, ma'am.
For calculation of the force, use the formula for pressure. How are pressure, force, and area related to each other? Because information of area is provided to you, force has to be calculated, and pressure you've already calculated.
Yeah, ma'am. Ma'am, 4.12 into 10 raised to 5 Pascal.
How much is it coming? 4
0.12
into
into 10 raised to 5 Pascal.
10 to the power 5 Pascal.
Yes, ma'am.
Let's check it once. So force would be pressure multiplied by area, and pressure is this rho gh.
Yes, ma'am.
So rho gh into A. You've done it in this way.
Yes, ma'am.
So what is your area? How much area you're taking? See this portion,
Ma'am,
10 to the
I
power
took
7.
10 to the power 5.
Area?
Yeah.
Why? See, area is already given to you in the question. Read the question once again. It is written that the area of that window is 20 centimeter into 20 centimeter.
Yes, ma'am.
Length multiplied by breadth. That is the area is given to you. You just have to convert it into SI units. So
Yes,
this would be 400 centimeter square, and we don't need centimeter square. We need the area in meter square. So that would give you 400, and then this remove the centimeter square. This would be 10 to the power minus 4 meters square. So you have this quantity, you have this area now. So force would be simply the product of the area and this rho gh. Rho gh is basically our pressure, the pressure exerted by the liquid or the gauge pressure. So this would be 400 into 10 to the power minus 4 into 10 to the power 7. Or you can say 4 into 10 to the power 5 Newton. Fine?
Yes, ma'am.
Just note this down.
Okay, ma'am. Done, ma'am.
Now we have a concept of relative density. See, this relative density is also known as specific gravity. So if the question says specific gravity, so just know that it is referring to relative density only. So basically, relative density is the ratio of the density of the body to the density of water. The formula of relative density would be the density of the given body divided by the density of water at 4 degrees Celsius. This is the formula for relative density. See, the relative density is the ratio of similar quantities. So can you guess its SI unit?
Newton per meter square. Ma'am.
Newton per meter square. See, density, just try to recall strain. When we were discussing strain was the ratio between two similar quantities, length divided by length, volume divided by volume, means change in the dimension by the original dimension. So it was a unitless quantity. Similarly, the densities unit would be in the numerator as well as densities unit of water would be in the denominator. Means kg per meter cube would be in the numerator as well as kg per meter cube would be in the denominator. So since it is the ratio of similar quantities, it would be unitless.
Okay, ma'am.
And density of water I've already told you. Just remember this. This is 1000 because many times it's not given in the question and you have to use it, or gram per centimeter cube. Is it clear?
Yes, ma'am.
Like I say, for example, just to clear this topic, the relative density is given 0.8. So it means relative density is what? Density of the body divided by the density of water. So if I have to find out the density of the body and the relative density is mentioned, then the relative density of the body would be simply the product of relative density multiplied by the density of water. That is 1000. So the relative density of that particular body will be 800 kg per meter cube in this example, this particular example.
Okay,
Just
ma'am.
note these few points, then we'll do a question related to this topic only.
Okay, ma'am. Done, ma'am.
Just try this question based on YouTube. See, the question says, like, if this is Mercury, then this Mercury has separated the water column and the spirit. So the length of the water column is given, I think, 10 centimeters. This is water, and this is the and the length of this is given as 12.5. So this is the question, and you have to find out the specific gravity. So we have discussed what is specific gravity. Just try this.
Okay, ma'am. Ma'am, 0.8, ma'am.
Yes, right. 0.8. The relative density is coming as 0.8. Correct.
Okay, ma'am.
And it would be unitless. Okay,
Yes,
see,
ma'am.
I'm adding another part to this question. Try that one. Do you know the density of mercury?
No, ma'am.
It is 13.6 into 10 to the power 3 kg per meter cube. So if you need this, you can utilize.
Can you please explain this one? I'm not getting it, ma'am.
Okay, I'll explain. See, now how much water and spirit have been added? 15 centimeter in each of them. And 15 centimeter in this also. In both the water as well as spirit has been added. So what would be the length of the water column now? 10 centimeter was already there. Now you have added 15 centimeter more.
25.
25 centimeters. So now the length of the water column is 25 centimeters. And what about the spirit side? This portion. 15 centimeter has been added and 12.5 centimeter was already there. $12.5 plus 15. How much is it? It's 27.5 centimeter. Yes or no? Yes,
Ma'am, can
Zoha?
you hear me, ma'am?
Yes, I can hear you.
Okay.
Oh, you were speaking.
Yes, ma'am.
I wasn't able to hear you.
Okay.
See, now the length of spirit column is 27.5 centimeter and the length of water column is 25 centimeter. So this much portion is clear to you. Now see.
Yes.
Now we have taken the way you did the previous question. It's similar to that only. See, now we have taken a point, let's say over here. Now Mercury must have risen up till this point also. Let's consider a neutral point, PA and PB. Since the height is same, the pressure would be same. You must have done this way only the previous question. You must have taken the pressure equal on both the sides. That's how you have got 0.8. Yes. So similar to that only. Now see if PA and PB are at the same level. These 2 points, PA and PB are at the same level. Now Mercury have risen up because of addition of water column on the side also. So I'm not drawing that. PA is equal to PP because A and B are at the same level. This is point A. Let's take this point as B. A and B are in the same level. Now see what will happen is that let us take atmospheric pressure also. P naught for this column. This water column.
Yeah, ma'am.
See P naught plus. Now let us take for water. So that would be equal to height of what H rho g is there. So H for water means height of water. Rho H rho g. So rho would be of water and acceleration due to gravity. That completes your first term. the arm given in the left hand side. Now let us take the right hand side. Now see, in the right hand side, the Mercury side has risen up. So when you're
Yes.
considering this point B, now not only spirit is there, but we have Mercury also. So there would be height of this Mercury column as well, which we have to calculate. We have to find this difference in the level of Mercury in the two arms. So Mercury has risen up and we have to find out this next. So when we took point A, only water was there, the fluid in that respective length. So we have considered the atmospheric pressure and the pressure exerted by this water column. But when we are considering this point B, we do not only have spirit, but we have Mercury as well as the spirit. Yes or no?
Yes, ma'am.
So now see, on the right hand side, we won't be having only what? Only spirit. It would be P naught for spirit, the atmospheric pressure for spirit, plus height of spirit, I'm taking it as S, then density of the spirit into acceleration due to gravity. Plus now the component, the pressure exerted by the Mercury column. So that would be height of the Mercury column. This is the unknown which we have to calculate. Then the density of Mercury column multiplied by acceleration due to gravity. Is it clear or not?
Yes, ma'am.
Now see, atmospheric pressure won't be, because the atmospheric pressure on both the sides are equal. Same atmospheric pressure has been applied, and acceleration due to gravity would also cancel because it is the same now. So see, height of water column we already have, that is 25 centimeter. So that would be 25 into 10 to the power minus 2, 25 centimeter. Density 1000 kg per meter cube. So this completes your left hand side, is equal to height of spirit now, that is 27.5 into 10 to the power minus 2. That is the height. Now the density for the spirit, which you have already calculated in the previous question. This was the question. So now you already have the value. What was the value that was coming? The relative density of the spirit. That was 0.8. Exactly. So now to convert it into CG SI unit, you multiply it by 10 to the power 3. Plus height of Mercury. This is the unknown variable which we have to calculate. Into density of Mercury is already provided to us in the question, or you remember this also as well, along with the water's density. This is 13.6 into 10 to the power 3 kg per meter cube. So from this equation, will you be able to find H? Height of Mercury.
Yes, ma'am.
Just try this after the class. Your answer should match with this. 0.22 into 10 to the power minus, approximately this.
Okay, ma'am.
So then note this down.
Okay, ma'am. Done, ma'am.
Now we have another law, which is known as the Pascal's law. See, an increase in pressure at one point of the enclosed liquid at rest is transmitted equally to every part of the liquid and to the walls of the container, provided the effect of gravity is neglected. There's a statement of Pascal, so I'll explain you how. I've written these important points also, note them also. First, understand. See, pressure in a fluid at rest is same at all the points. This is also a very important point because this would help you solve the numericals as well. Now, Pascal's law of transmission of pressure. A change in an enclosed incompressible fluid is transmitted undiminished to every part of the fluid and walls of vessels. And the pressure exerted at any point in an enclosed liquid is transmitted equally in all directions. This simply means that I have taken a spherical vessel. For example, I've taken this spherical vessel. and I have filled it with a fluid. This is one level of the fluid, this is the second surface, and this is the third. Now tell me, if A is the area of this, let's say this is the first end, A is the area, F is the pressure exerted. So if I have exerted a pressure on this column, then this portion of the liquid will exert force or pressure on the end of this, and this liquid will also be pushed towards this end. Yes or no? If I have applied a force in this direction only. Yes.
Yes, ma'am.
So what would be P1? Pressure over here at this end. Let's say this is second end, this is the third end. What is the pressure over this end? F is the force applied and A is the area of the cross section.
F by A, ma'am.
F by A. Pressure over here is F by A. Now see, Pascal's law says pressure in a fluid at rest is same at all points. And the transmission's law says that a change in an incompressible fluid is transmitted undiminished to every part of the fluid and walls of the container. It means now let's say the area of this is 2A. All right. The area of this end 2 is 2A. So now see what would be the force. Pressure would remain this only because pressure is same. So now see, pressure 2 of this portion should be F2, whatever is the force, F2 divided by 2A. According to the rule, pressure is equal to force upon area. Now see what would be this force. Since these pressures are equal, F by A would be equal to this F2 divided by 2A, equating this with this. Yes or no? This is clear?
Yes, ma'am.
So F2 would be twice of the force, so as to equate the pressure. Understood? So for
Yes.
example, let's take this third end, and let's say the area of this third end would be 3A. Can you tell me what would be the force?
3F, ma'am.
3F, exactly. 3 should be F3. Let us say F3 is the force exerted over here. So it should be F3 divided by 3A. So again, you can equate it with this. So this would be F by A is equal to F3 divided by 3A. F3 would be equal to 3F. So the force would increase because the pressure has been transmitted undiminished, means there has been no change in the pressure. So have you understood these points which I was dictating?
Yes, ma'am.
Just note this down.
Done, ma'am.
See, hydraulic lift, a practical application of Pascal's law is the hydraulic lift. Hydraulic lift is used to lift heavy weight. So see, what happens is that in the construction of it, it says that it consists of two vertical cylinders. Let's say this one is A. Let's take this one as B of different cross sections area. Let the cross section area of this A side be A1 and the cross section area of this B portion be A2. Fine. So A1 is there and A2 is there. Can you compare them? Which is greater? By looking at the figure only.
A2, ma'am.
A2 is greater than A1. So A1 is the area of smaller cube, whereas A2 is the area of larger. So A2 is clearly greater than A1. Now see, these two vertical cylinders are connected by a small cylinder over here, placed horizontally, connected by a horizontal tube. So let's name it as C also for our convenience. Now see, pistons are fitted in both the cylinders. Over here, pistons are fitted in both the cylinders. And the system is filled with water or oil. The fluid is filled over here. The load to be lifted is placed on the cylinder having larger cross section area. The load like car, when we have to lift heavy objects like car or whatever is the heavy object, the load is placed in the cylinder having the larger cross section area. And the lifting force is applied at the smaller cylinder of the smaller cross section area, A1. So see, when downward force F1 is applied to the smaller piston, let's say this A piston, the pressure of liquid under this piston increases to, what should be the pressure? F1 is the force, downward force acting, A1 is the area of cross section. P should be
F1 by A1.
F1 by A1, yes, F1 by A1. So according to Pascal's law, whatever we have learned just before, this increased pressure is transmitted to every part of the fluid, every part of this liquid, including this piston B. So you can say this pressure F1 by A1 or P is exactly exerted on B point as per Pascal's law. So upward pressure, upward force on this, because it is used to lift this. So the upward force would be, see, upward force should be the pressure, this pressure only, multiplied it by its area. Or you can write F2 is equal to, you can put the value F1 divided by A1 multiplied by 8. Yes?
Yes, ma'am.
And this force is greater. F2 is obviously greater than F1. That's why the small force is helping us to lift heavy objects without any manual effort.
Yeah.
This is basically the practical application of Pascal's law, which has been used. Hydraulic lift. Just note this down.
Okay, ma'am.